Welcome to the 15th lecture for NPTEL course on computer system optimization for machine learning. As usual, we will give you a brief recap, and remember that we are talking about DNN accelerators. In the last lecture, we talked about DaDianNao, and in today's lecture, we will see the other variations of DaDianNao, the other series of the other accelerators in the DaDianNao series, and then if time permits, we will talk about Eyeriss. Okay. A brief recap, we talked about the DaDianNao accelerator architecture in the last lecture. It has the split buffer, it has three different storages. One is to store the inputs, other is to store the synapses, the other one is store the outputs, right. So, again as a reminder, we have three split buffers, and that is why there is no conflict. So, the access latency is less. They have neural functional unit, and the neural functional unit also has three distinct component. One is NFU1, which consists of multipliers, NFU2 which consists of adder tree, and then NFU3 which consists of nonlinear unit. And finally, they have this control processor, which is responsible to perform the control instructions, or to store as well as to schedule the control instructions. Now, we saw DaDianNao. Next, let us discuss DaDianNao. In Mandarin, DaDianNao means a big computer. So, if you remember, DaDianNao consists of a single NFU unit, right. There is only one of this NFU unit, where we have a bunch of multipliers, bunch of adders, and then bunch of nonlinear operations, or bunch of units which compute the nonlinear operation, right. Now, definitely it is not suitable for executing large DNNs. So, if you remember, I was showing you one table where I showed you the the number of MAC operations as well as memory accesses for different DNNs, and there we saw that the number of MAC operations can be as high as like billions, correct. So, definitely just having one set of neural functional unit is not sufficient to execute large DNNs, right. So, that is why DaDianNao integrates many of these DaDianNao NFU on a single chip. So, you can think now we are going from a single core processor to multi-core processor, right. Now, again the idea is similar. So, there are synapses close to neuron, and then in DaDianNao they have EDRAM instead of SRAM. So, EDRAM is more energy efficient with respect to SRAM. Now, let us see the high level architecture of DaDianNao, or sorry, the high level architecture of DaDianNao. So, this particular figure is showing the EDRAM placement, right. Now, we can see that there is a NFU unit in the center. Now, each of these NFU unit is connected to 4 EDRAM banks. Okay. Now, in these EDRAM banks, the synapses, the weight values are stored, and these synapse rows are interleaved, so that we can seamlessly access the synapses from different EDRAM bank. So, that is the high level, or not high level, actually this is more granular level structure of the NFU. In earlier DaDianNao structure, if you remember, NFU was there, and then we have 3 different buffers. Still we have 3 different buffers, but these EDRAMs are used only for synapses, and then these synapse rows are interleaved, so that the access latency are less, right. Now, this is the high level architecture of DaDianNao, where you can see that it is a tile based architecture. So, you can see that this is the top level architecture of DaDianNao, where we can see that there are multiple tiles, right. We have 16 tiles in total, and then there are 2 central EDRAM banks with fat tree interconnect. So, there are central EDRAM bank where we have, this is the fat tree interconnect, which is connecting these tiles with the central EDRAM banks. Okay. Now, again inside each tile, as I already told you in the previous slide, we have this NFU which is connected to this 4 EDRAM banks, which is storing the synapses. Okay. Now, as I was saying that in DaDianNao they are going from single core to multi-core, correct. Now, whenever we have multi-core architecture, the main issue or the main hardware component which we need to think about multi-core architecture is the interconnect, right. If we have multiple cores, then we need to actually connect all the cores. If we do not connect the cores, then the cores won't talk. So, we cannot have like coordinated computations with all the cores, right. So, similarly, in DaDianNao architecture, they have interconnect for all the tiles, and that is a mesh NOC having routers with 5 by 5 crossbars. So, let us step a little back, let us take a step back and then let us discuss what is this mesh NOC or the interconnect architecture, right. So, this particular figure is showing a 4 by 4 mesh NOC, or we can think that there are 4 routers in this particular NOC. Now, we can imagine that each of the router is actually connected to one of the tile. Okay. So, in the previous one we showed you that there are multiple tiles. So, there are 16 tiles in total. So, we can think that each of these routers are connected to one tile. Okay. Now, whenever one tile needs to send data to another tile, it will first send the data to the router will send the data to different router, and finally, the data will reach to the destination. So, that is how this on chip communication happens. Okay. Here we assume YX routing protocol, that means the data is first going in the y direction and then it will go to the x direction, right. Now, whenever we have this router based NOC, remember towards this router there can be many data, or let us say let us take another router in between. So, this router can have a data from north, it can have data from east, it can have data from south, it can also have a data from west. Not only that, at the same time it can have data from the tile which is connected to this router, correct. Now, it can have data from all 5 direction, and then the data also may want to go to all 5 direction. Data may want to go to east, to south, to west, to north, as well as to the self phone, right. Now, in that particular case, we need to know how we can route the data, right. We should have a proper routing protocol, or we should have a proper data forwarding protocol, right. So, in short, there can be 5 input port and 5 output port for each of the router, right. Now, for each input port, so that is why now this particular figure is showing what is there inside the router. You can see that there are multiple input ports and then multiple output ports. Now, data has to be routed from one particular input port to another particular output port, and there is a crossbar structure. So, crossbar structure you can think it is some giant multiplexer which routes the data from one particular input port to another output port, right. Now, inside router there are multiple pipeline stages. First the data comes, then it goes through input buffering, then route calculation as well as switch allocation happen, then switch traversal happen, and then link traversal happen. So, these are the different pipeline for the router. Okay. So, overall what I am trying to say that whenever we have multi-core architecture or the multi-tiled architecture in case of DaDianNao, we have to actually connect all the tiles, right. We have to connect all the cores in the multi-core architecture. Now, the best way to connect, or the state of the art way to connect all these multi-core architecture is this NOC. Okay. You take any of the state of the art processor like maybe Xeon processor from Intel or AMD's EPIC or Ryzen processor, they all have this NOC, they all have this network on chip architecture. Okay. So, similar network on chip architecture was used for DaDianNao also. Now, in this slide I am showing the high level diagram of the 5 by 5 crossbar architecture. As I was saying that this crossbar architecture takes 5 input and 5 output. So, inputs are nothing but north, east, south, west and self, right. And then each of the crossbar also has like 5 output, or the router has 5 output north, east, south, west and self. So, inside the crossbar we have like giant multiplexer. Okay, there are many multiplexers and then controls which determine which output should go to which input should go to which output. And the biggest advantage of the crossbar architecture is, let us say there are 3 different packet in north, east, south, and then let us say the packet which is in the north, they want to go to south direction, the east want to go to self, and south want to go to west. So, all these 3 packets will be routed at the same time. So, there is high parallelism, and that is the role of the crossbar architecture, to introduce this parallelism. Also, there are virtual channels which reduce head up blocking. So, there are more advanced architecture of NOCs which probably take little more resource, but then improves the performance a lot. Okay. Now, that is the thing, that is the main thing in the DaDianNao architecture, DaDianNao architecture, where they have taken one NFU unit and then scaled it up, right. Now, this is the layout of DaDianNao architecture, where I already showed you there are like multiple tiles, and then there is a central block which is nothing but that fat tree which is connecting the central EDRAM buffers to all those tiles. Remember, there are 2 interconnect here. One interconnect is connecting all the tiles, like there is some data movement between the tiles, and then there is another fat tree interconnect which is connecting the EDRAM buffer with the tiles. Okay. Now, these 2 figures are showing some results, where the results are showing for 1 chip, 4 chip, 16 chip or 64 chip. When they say 64 chip, that means they are integrating 64 DaDianNao chip. Okay. Now, as you can see that this particular figure is showing the energy reduction with respect to NVIDIA K20 GPU, right. Now, as you can see that all the variants, like all 1 chip, 4 chip, 16 chip, 64 chip variant reduces the energy consumption, like if, because all the numbers are more than 1, right. Now, when we go from 1 chip to 64 chip, you can see for some of the layers the reduction in the energy consumption is less, right. Why the energy why the energy consumption or the energy reduction is less? Because when we integrate multiple chip, then there is some overhead, the overhead of the interconnect, right, the overhead of the data access from EDRAM. So, that overhead might be more than the actual computation overhead. So, it will end up resulting in less reduction in terms of energy, and that is what it is happening. But the advantage is, for some convolution we have to use 64 chip, otherwise we cannot perform that convolution with just 1 chip, 4 chip or 16 chip version. Now, that is in terms of energy. Now, when we see the speed up, you can see that speed up is almost always increasing with respect to like the lower chip version. So, when we go from 1 chip to 64 chip, you can see that there is the speed up is increasing from 1 chip to 64 chip, and there are some cases where the 1 chip, 4 chip or 16 chip versions cannot even handle that much computation, right. But again, in this case also you can see that for classification layer, 64 chip might not have much improvement with respect to 1 chip, 4 chip or 16 chip version. So, again there is a trade off. Yes, we can use multiple tiles, we can use multiple core, but then there is a trade off, correct. So, that is the DaDianNao architecture. And then finally, let us discuss the ShiDianNao. In Mandarin, ShiDianNao means vision computers. So far we have seen just an accelerator architecture which performs convolutional layer operation or convolution CNN execution, right. Now, those architecture, either DaDianNao or DaDianNao, they are not curated for any application. So, finally, this ShiDianNao is curated for a specific application. So, there are additional components like ALU to incorporate different activation, and there are instruction buffers. So, now as you can see, they are now going towards a full fledged computer or full fledged accelerator. So, in ShiDianNao they have proposed a specific data flow, they have an algorithm to hardware mapping, like given one particular algorithm which PEs or which NFUs should be used, and then finally in ShiDianNao they are able to execute the whole DNN instead of a single type of layer. So, in the previous one in DaDianNao or DaDianNao, they were only executing one single type of layer, be it classification or be it convolutional layer. And also in ShiDianNao, they have shown real application like facial recognition, handwritten digit recognition through this particular architecture. Okay, I am not going into the detail of ShiDianNao, but you are encouraged to read the original paper and see what are the other intuition they have brought out from different applications. Like as you can see, so finally they have used the accelerator for different application rather just to show the performance of different layers of a CNN, right. So, overall so far we have seen the DaDianNao series. The very first one, DaDianNao proposes like split buffers or proposes one accelerator architecture where we have split buffers and then we have 3 different NFU unit. DaDianNao scales up DaDianNao into multiple cores and then ShiDianNao executes specific applications like facial recognition and handwritten digit recognition. Now, finally, let us discuss about Eyeriss. So, Eyeriss is an energy efficient reconfigurable accelerator for deep convolutional neural network. So, pay attention to this word reconfigurable. So, whenever we say reconfigurable accelerator, that means the architecture will of course remain the same, but then the different part of the architecture will be used differently based on the input parameters. Okay. Now, in Eyeriss there are many new things. One is there is a new data flow, then the architecture is new, there is a new encoding and decoding technique, and finally it is a fabricated chip which is a coprocessor. So, in this particular slide I am showing you the overview of the architecture. So, there are 2 clock domains. You can see there is a line clock and then there is a core clock. So, again as I described in few lectures back. So, clock is nothing but you can think that at each cycle or at each tick some processing is happening. Okay. More the clock frequency, the faster the processing is, correct. So, in Eyeriss they have 2 clock domain, link clock and core clock. So, remember the core speed can be different than the DRAM speed. So, that is why they have 2 different clock, which is one is operating between the DRAM and the accelerator, and then there is another separate clock at which all the internals or all the processing in the accelerator is happening. Now, as you can see, I mean we will go into the detail of the accelerator very soon, but at a very high level it has 12 by 14 PE arrays. Now, PE is nothing but processing element where they have scratch pad, multiply, accumulate operation and then some control, right. Apart from PE array they have this global buffer, then they have some top level control, they have some encoder and decoder. We will also go what encoding and decoding is going on, but overall there is a huge amount of communication. There is a communication between the PE and the global buffer, there is a communication between the PE and then there is a communication between the scratch pad and the PE, scratch pad of one PE to scratch pad of another PE, right. So, there are a lot of communication. So, whenever there is a communication we need to see how to optimize the communication, right. So, again there are 2 levels of controls. At the top level there is traffic between the DRAM and the global buffer, and then there is a traffic between global buffer and the PE array. Okay. So, there is a traffic between this global buffer and then this PE array. That particular traffic is handled by the network on chip as we discussed during the DaDianNao. Okay. Then there is operation of this RLC, we will see what is this RLC decoder and encoder. There is operation between this RLC and the ReLU unit. So, there are multiple levels of control or multiple levels of communication going on, and then there are lower level of control, there is control logic in each PE. So, inside in each PE there is control logic as you can see, and then these PEs can execute independent of each other. So, each PE starts processing whenever the feature map or the partial sums arrive. do not confuse between this PE array with the systolic array which we discussed few lectures before. This is not like systolic array. So, in systolic array whenever the data started flowing, all the PEs will start executing. Now, unlike here, each PE starts processing whenever the feature map as well as the partial sum arrives at each PE, not necessarily the entire PE will operate at the same time, right. Now, the main flavor of this Eyeriss architecture is the data reuse. It proposes a new type of data flow which we will see very soon. Now, before that, let us spend little time behind data reuse. Again, this particular figure is showing the regular convolutional operation where we have m filters, each filter of size r by s by c, and then we have input feature map where each of the input feature map is of size h by w by c, and then we will have total n input feature map. The whole convolution process is generating generating output feature map of size e by f by m. Why we have m number of channels in the output feature map? Because we had m number of filter here, right, and since we have n input feature map, we have n outputs, right. Now, if you look closely, how many times a filter is reused? E by f times, right, because each of the filter will actually convolve E by f times to generate each of these pixel, correct. So, that is why each of the filter is reused E by f times, and how many times an input feature map pixel is reused? R by s times, right, which is the same in the same filter plane, correct. So, whenever of course, the corner pixels will probably get reused less number of time, but if you think about any middle pixel any pixel in the middle of this input feature map, they will get reused by the filters r by s times. So, each of the value of the filter will actually pass through this input pixel, right. Now, each filter weight is also reused across the batch of n input feature maps, right. For each of these n input feature map, we will use the same filters again and again, correct. So, that is another type of reuse. And finally, each input feature map, each of these input feature map is reused across all these m filters, right. So, these are all the data reuse, or these are all possible data reuse in convolutional operation, right. Now, the idea in Eyeriss is that we have this c by r by s partial sum, right. So, all these c by r by s partial sum values must be computed as soon as possible. So, whenever we convolve, like this c by r by s is convolved with this input feature map, then we will compute this c by r by s partial sum, and then all those partial sums will get added to produce one pixel in the output feature map. The idea in Eyeriss is to compute this c by r by s partial sums as soon as possible, okay, like at one go maybe. That will minimize the storage and data movement. Now, let us see how it is possible. So, towards that goal, Eyeriss proposed something called row stationary data flow. Now, in row stationary data flow, each primitive, we can think primitive is nothing but that processing element, the PE. Each primitives operate on one row of filter weights and one row of input feature map to produce one row of partial sums. So, earlier we talked about output stationary data flow, weight stationary data flow, input stationary data flow. Now, Eyeriss proposed something called row stationary data flow, where they are trying to compute one row of output feature map at one go. So, let us take the example of 1D convolution, where let us say we have this filter row, we have this 1, 2, 3, these are nothing but the indices of the filter row, and then the input feature map row is 1, 2, 3, 4, 5, right. Now, let us say we have one processing element which performs multiply and accumulate. So, first this 1, 2, 3 will be multiplied element, will we will perform element wise multiplication between this 1 to 3 and then this input feature map 1 to 3, and then if we add we will get first partial sum, right. Now, in the same PE we will again have multiplication or element wise multiplication between the 1 2 3 index of the weight and the 2 3 4 second third fourth index of the input feature map to obtain the second partial sum. So, similarly we will obtain the third partial sum. That is how, and once we have these partial sums, then we can say that one row of output is produced, right. So, that is the philosophy of row stationary data flow. As you can see that we have one particular PE. So, all these things is happening in one particular PE. So, if you remember, the PE is nothing but one MAC unit, they just perform multiply and accumulate operation, right. So, one particular PE, in one particular PE we have pushed all these filter weights and then all those input feature map values, they will perform the multiplication and then addition to perform to obtain one partial sum. Okay. And then again we will have the next set of input feature map values, which will again will be performed element, we will perform element wise multiplication to obtain the second partial sum and then the third partial sum, right. Now, of course, there can be like multiple of those channels. So, that is why these are the partial sums, so that we can add across multiple of those channels, right. So, this is the main idea behind the row stationary data flow. Now, in the next lecture we will see how this row stationary data flow will work in case of 2D convolution. Okay. So, till then, thank you, see you next time, bye.